So basically, Flux app consists of a Python backend and a TypeScript frontend. And the spiking neural network itself runs on web GPU, which makes it cross-platform and makes it easy to launch it on any device. So let's go into the interface. Okay. So I wouldn't tell you a lot about the general things like the organization settings and the profile settings. Is pretty much understood. So let's just focus on the editor itself. So basically we call it a Figma for spiking neural networks. So in the top section we see like high-level controls. So like here we can create new circuit, manage our organization, manage users, see notifications, and open Explorer, for example, and also control the circuits, change them, and undo or redo actions. In the bottom section we see an execution control, which lets us switch from live mode to disabled mode. Also it lets us control the speed of the network, and also has 3 levels of visualization depending on which kind of visualization you need. Okay, so this is just a very simple network, and let me create a new one. Oh no, sorry. So first about the interface itself. So basically on the left we see a tree. So this is basically a circuit tree because as it is said, Flux is built around the component architecture, so you can create some circuits, repeat it once, then arrange them into components and build a deeply hierarchical structures so that you can treat your artificial nervous system as a regular programming system, a well-designed programming system. On the right, we have general settings of the project, like environment variables, plugins, and organs. About organs, I'll tell you in a bit. And in the center, we have like the central control board, like the one we have in Figma, and a couple tools like Zoom and switch between modes, etc. All right, so now let's go into the new one. So let's create a new network. Test demo. Network, and here we can add some markdown description, like, okay, we won't do this, but you can do this. And actually this is the language where which like the way by which you can describe any component that you create and share it with the community. So it's like a full-featured markdown editor. All right, let's create the new one. So it's a demo network, and let's go and create something that's actually working. Like, let it be a central pattern generator, for example. So in biology, this is kind of the major building block of the brain's dynamics. So basically it's just recurrently connected neurons that have some sort of an oscillator activity inside. To do this, we need to create 3 neurons, connect them with 3 synapses, and then add some controls so we can start this generator and stop this generator. So let's go and create 3 neurons. So here we are in edit mode, and once we click anywhere, we have this window which lets us create 3 types of nodes. These are neurons, circuits, and organs. Let's go with neuron first. So here we have a bunch of settings, but we'll go with the default ones now. Okay, so we create one, second one, so let's just move it over the grid, and the third one. Okay, now we have 3 neurons. We can move them around, zoom them in and out. Now it's reflected in our network, good. So now let's connect them with the synapses. So now we have one synapse that points to this neuron. So you see we have this gradient that illustrates the direction. Then we have the second one and the third one. All right, so now we have a central pattern generator. So each synapse has a delay about 100 milliseconds. Well, not about, but 100 milliseconds, and a weight of 10. Okay, so now we need to make this work, right? And this is where the organs kick in. So basically, an organ is how we call a type of extensions for the network that either accepts some input in the form of spike trains or generates some output in the form of spike trains. So basically, it is the way for us to connect to our network. So for example, if we want to create some interface, or we want to read some sensor data, or we want to control the server, or we want to run some deep neural network that is not spiking or stuff like that. So basically any sort of computations that you can do. And it has a neuron interface to either generate spike trains or receive spike trains. So to make this network work, we need one simple organ that is called keyfire. So basically it will just fire anytime we press a key A. And as you see, it has one output neuron, that is its output interface, and let's connect this to this guy. And now what happens if you press A? You see, it fires. So basically this organ is pretty simplistic and just fires a neuron once you hit a key. Okay, so still the threshold is not passed, so it doesn't do anything. So let's double tap, and you see, yeah, let's go. Okay, so it's going now. As you might have noticed, it's a little bit different from a regular spike in neural networks because we do not flush the level when the neuron fires. It is made to fit with the biological counterpart because, in fact, in biology, neuron doesn't flush the mediator in the space, because in our opinion it is by mistake that we do the flush, because what actually happens is the mediator level change and it doesn't get affected by the actual firing. But anyway, if we want to get a more classic behavior, we also have a fire price property, which is 0 now, but if we put it, for example, the same as the threshold, then we'll get a regular firing behavior, flushing behavior. Alright, so now it just runs and doesn't do anything, so let's do something that pauses the guy. Let's create another organ, another key fire, but let's do it a W. And let's create a synapse. So as you see, there are 3 types of synapses, but for now we use only drivers, which basically modulate the level of the neuron. And let's give it an amount of -50. So now, as you see, the width of the synapse reflects the strength, so the weight, and the color, it reflects either it's inhibitory if it's negative, or excitatory if it's green. Alright, so it's W, and you see it just drops the level down. So let's start it, and now we have an ability to kind of pause this one. So if we just inhibit this guy, once this level reaches below the threshold, it just stops. The generator stops. Okay, so far so good. So alright, so now we have created kind of generator that we can start and we can stop. But in biology, for example, what if we want to make this oscillate faster or slower? Regular neural networks, spiking neural networks, they do not have this ability, but our network is based on a neuromorphic architecture. And this is why we are introducing the new type of synapses that are modulatory. So modulation is something that doesn't really change the level that makes the neuron fire, but it changes its properties. So in case of a neuron, first let's create 2 more organs, 2 more key fire organs that will fire on S and they will fire on D. There it is. Okay, D. And now let's make a synapses to all of the neurons, but now we pick the modulator. You see it's displayed as a dashed line. Oops, let me change this and update. So we have created 3 excitatory modulatory synapses. And now let's create 3 more, which will be inhibitory. So the same, but in minus. Okay. So we have 3 of them. Alright, so now let's launch our generator and we see it start working. And now if we excite you see this halo, it depicts the modulation level. It starts oscillating faster. I don't know if we can see it on the screen recording, but anyway. If we inhibit, then it starts oscillating slower. So this is basically a way to control the activity of our networks without basically changing the structure of the network, and this lets us resolve these things with a much better precision and use much fewer neurons to operate. Alright, so what we did, so we just created a central pattern generator. Looks a little ugly. Let's move it around. Okay, and okay, so in a real networks we can have like hundreds or thousands of such generators, and we can build any type of activity, any type of behavior with them. You can think of Fourier transforms, for example. And what if we want to reuse it for future? So we would just want to group it. In this case, we can select and name it CPG. And create a group. So now it looks like this. I mean, not group, but circuit. It looks like this. So now it's a separate node. And we can create a neuron that interface with this node. We can have this activity and put it somewhere else. Also, we can clone it, for example, like that. Right? Another thing is, for example, if you want to have a connected circuit. So, for example, we want to duplicate the circuit, but we want to have the changes propagate to all the duplicates. And we can do it by grouping them like that. So we can give it a color and say group 1. Okay, now we see this link, and if we change one node, the other one gets changed too. And now we see them displayed in our hierarchy tree, and we can expand it. Also, we can just go and open it up in a separate tab and modify it separately. So basically, it can be stated as a mix of Figma and VS Code, for example, but for building the spiking neural networks. Okay, so far so good, but this is very simple. Let's go to something that really works tough. So let's go and check the locomotion system for our hexapod robot. So here's how it looks like. We made it look like that. So we didn't group, for example, this elements so that it's easier to see what's going on. So let's just launch it and see. So here's the interface to launch. So yes, let's go, and what is the key to launch? It's Q. Okay, let's go. So you see now we get the activity going. So first it goes on the left side and moves the left legs. Now it goes on the right side and moves the right legs. Each organ here controls a servo, and they are connected with via WebSockets to the actual hexapod, so they connect the data in real time. So what these servos do is they read the data from the spider. They also display the tension on the muscle. Now the spider is not connected, so we don't have any tension here, but it just displays the actual level of the servo. And yeah, so basically this makes the hexapod run. The next steps here is to create read the sensor data and propagate in the network. So for example, if it gets the proximity signal from the LiDAR sensor in front, then it stops and tries to turn around. This is pretty easily resolved by modulation. And next steps will be to create a reinforcement learning system and give him some sort of values and desires so that he can do something meaningful, like chasing the red ball. All right. And yeah, so I promised not to be technical, but I just want to tell you about how it's structured, because this is one of the great parts of the system. So let's just turn it off. Let's go into the code and let's see how this servo muscle is engineered. So each organ is an extension, and first we describe the interface. So this is the module that can be created by any developer and deployed as a regular npm module. So in it contains two files, the definition and the organ itself. So in the definition file, we first describe the schema, so the settings that we prompt the user to put, and then the neuron interface. So there can be neuron and output neurons that will actually either receive or generate spike trains, or do both as in our case. So in the case of servo, we need to send it a tension, and we need to read the several parameters from the server, like the tension on the server, position of the server, temperature, load, speed, voltage. So these are the signals that are getting sent by the ESP32 and from the servers, and we convert them to spike trains in the organ. So this is the definition. The next is the organ body itself, and it extends the organ class. So here we were inspired by React functional components, and this is basically also has a reactive state. In the setup function, which is predefined, we have all the initialization logic. So in this case, we subscribe to engine event, which is like a neuron firing, and we convert this signal to tension. And in the update tension, we send this to the server. Another thing is it has a render method, which is also quite familiar for React developers, and this lets us have any sort of display for those servers. So basically, what you see here is a React component, and we can build any React component that is, well, just anything that you can build in React, you can build with the server. So it lets you create any interface, and this interface will be displayed in the dashboard, which is like a second mode. All right. So thank you for the quick overview. I hope it wasn't too technical and too boring. And so what's next? So now we are working on the GPU side. So we make it work with web GPU. We have reworked the architecture completely, and now we're implemented it, and we already have really great results in terms of performance. So we can run a 1 million neuron network on a like mass market machine. The second thing we're actively working on is the cloud protocol that can connect networks on the networks on the network. Yeah, so like and enforce like make it use the cloud computing to scale horizontally. Because what's cool about spiking neural networks is they have a natural delay in synapses, and this delay can be compensated by it can compensate the latency, and this is something we are actively working on, like the node discovery and all this stuff. On the interface side, we are adding a version control system, so something like a simplified Git, so that you can branch out from the original circuit, try something else, do some commits, and then merge it to the master one. And also we're working on the interface to have some bigger nodes, so inspired by, for example, graphic engines, like Unreal Engine, for example, so that you can have nodes and you can connect them. So in this case, you can have some neuronal populations, like 100,000 neurons, like liquid state machines or anything else, and then connect them all together. Yep, so that's it. Hope it was interesting, and thank you for your time.